Recording is rolling. Welcome to Friday, October 22nd. So you guys picked up your centrifugal force and gravity quiz from those folders back there. You guys did find that, right? So got a new handback system. I'll post the solutions to those after school. So see those. If you need to do corrections, just like last few quizzes, then that'll be available. Handwrite those and turn this in if you need to. Okay. So we're going to go over as many Chapter 5 puzzles as we can today. So energy and work. Oh, also, don't forget your guys' Unit 3 multiple choice questions have been open on AP Classroom for a while. I did bump the due date by a day because that's what we're doing. Okay? So just by Tuesday. All right, so Chapter 5 puzzles. First one, a weightlifter lifts a set of weights. Now, okay, they straight gave you the weight in newtons. Okay, that's nice, because they could have said mass, and then you'd have to go the extra step of solving for the weight, but okay, they gave that to us. Okay. To a position over its head, a vertical distance of so many meters. How much work did he do, assuming the weights moved at constant speed? Okay. Oh, side note here, I haven't really mentioned this, but see where it says assuming the weights move at constant speed? That's one of those little details that could show up on the AP exam. What if it was not constant speed? Like, what if he's lifting the weights faster, faster, faster? Do you think that would be kind of analogous to an elevator accelerating upward? It sure does sound like that, doesn't it? And if that's the case, then wouldn't the applied force be more than the actual weight of the weights themselves? It would be, which means you'd be doing more work. Okay. That's the idea of constant speed. If it's constant speed, that means if you make a free body diagram, isn't the applied force just equal to the weights in magnitude, so that it's like equal and opposite, just all the way up? Okay, so that's one of those little details that I never know when that's going to come up. Okay, number 1. Okay, so we're taking these weights. Maybe they look kind of like this. Okay. Now I'm gonna let's do a free body diagram. Right? So mg equals. I'm going to make up my own number. I'll call these 500 newtons. So to look at constant speed, that's the whole thing about constant speed. That means the applied force, like the lifting force, would be equivalent to that. And we're going to lift these things a height of, I'll have a short guy, let's say 1.50 meters. Right? What's the work associated with that? Right, so the work, you guys remember formula for work is force times distance, isn't that? Well, I've got this up here. Remember gravitational potential energy, MGH? Because those two are actually pretty closely related to each other for a question like this. So it's force times distance. Now that's a dot product, which means that only the parallel components are multiplied together. But in this case, those are the same direction, because the applied force is upward, the direction of motion is upward. Okay, so you don't have to do any trigonometry or anything like that. Okay. But the applied force, that is equivalent to the weight, isn't it? And the distance moved, well, that is a height because you're moving it against gravity. Hey, look at that, MGH. So the work you put into it is equal to the potential energy that it ends up with. Well, of course it is, right? So I've got 500 Newton weight, moving up 1.5 meters. So that looks like 750, what's the unit? 750 what? Joules, good call. How many joules? You did that much work lifting it, expended that much energy. That's it. Okay, number 4. A shopper in a supermarket pushes a cart. Ooh, this sounds a lot like an example problem you guys got in the notes a few days back. There was a good reason to give it to you. With a force of so many newtons directed at an angle so many degrees below the horizontal, that picture I gave you guys in the notes the other day, I'm just going to redraw that picture because same story. The force is just sufficient to overcome various frictional forces so the cart moves at constant speed. We're going to make a free body diagram while we're at it just to think about how that works out. Find the work done by the shopper as it moves this many meters down the aisle. And then, well, there's a follow-up question, but let's do one at a time here. Number 4. Let's get a big old grocery aisle going. Get a shotgun cart. Got some shotgun cart wheels. Yeah, think about free body diagram of what's going on. Now, from that center mouse dot, we had to put a dash line parallel to the ground just to get an axis going so we can make sense of this. All right. So I know that this cart is going to have a weight. I call that mg. I know, I'm not going to put the normal force yet because, well, you guys see why. Let's do the applied force next. The applied force was some force below the horizontal, right? So I'll call it F push, right? And it's some angle of theta below the horizontal, right? Now, do you guys see what I'm about to do? I'm going to switch color again to like this light blue color. Okay? I'm going to split this force vector into components. Now, what I'm about to do, probably avoid doing this at all on an AP exam. If you really have to do it, either do it in lim and eq or like dash the vectors. Like, maybe both. Dash and lim and eq. Because pushing down to the right, well, pushing down does one thing and pushing forward does something different. Okay? Isn't this, what is this? F push times what? Sine or cosine of theta? Sine theta. Okay? Yeah, hopefully you guys are really comfortable with that by this point here. Okay, so this would be F push times cosine of theta. Okay, now let's go to the normal force. And I said I didn't want to draw that before because usually normal force is just equal to the weight, right? But this time it's not. This time the normal force is equal to what? Exactly. Right? Because aren't both of these pointing down? But if the shopping cart isn't accelerating up or down, there's no net force up or down. Ah, the normal force. Right. Now this is a little bit too detailed for the questions they're asking, but this could pop up. So yeah, no, that's exactly what you said. It's equivalent to the sum of the weight and the sine component of the pushing force. That expression. That's what it's equivalent to. Right? They did say one more thing. It's that there is a friction force so that the cart moves at constant speed. Do you guys see what the friction force must be equal to?
F push cosine theta?
Exactly. Yeah. F push times cosine theta. Now, side note here, they didn't go this way with this problem, but who knows what you're going to get on the exam. I meant to make the normal force significantly bigger than the weight. So this should be much bigger than this. Okay? Should be these two put together. Here's one way they could have gone with this, going back to a couple sections ago, is that you guys know friction force is also coefficient of friction times the normal force. So if you do F push cosine theta, that's equal to this expression times the coefficient of friction. Right? But let's not worry about that so much. Let's get to the actual question. They gave you some numbers, so I'm going to call F push an even 50 newtons. I'm going to say this angle is 30 degrees. These numbers are a little bit different than your book numbers, but not hugely different. And oh, also this cart was pushed a certain distance. So I'm going to say this distance D is, let's go 100 meters. Guess we have a grocery store that's like the length of a football field and all those groceries. What was the work done by the shopper on the cart? So you guys know work is equal to force times distance, but it's a special kind of multiplication. That's dot product, isn't it? Okay. Now, if you just go straight to the textbook definition, that's the magnitudes multiplied together times the cosine of the angle between them. You could think of it that way. You would get the right answer. Here's how I prefer to think of it, is that only this blue component, F push cosine theta, is actually doing anything. So F push cosine theta is actually doing anything. Okay. So that's the direction of motion, and then you just multiply by the distance. Right? You guys see that that is FD cosine theta? But with the commutative property of multiplication, you get a slide turns around. Right? Okay, so let's pop numbers in. I had a 50 Newton pushing force. Cosine of 30 degrees was my angle. Okay? And then I was going a full 100 meters. 50 cosine 30 times 100. Okay, so my numbers worked out like this many joules. How many joules of work were done by the shopper on the cart? Okay, you guys get that? Okay. So that shopper put that much energy into the shopping cart. Okay. Now, there's something called the work energy theorem that says that the work you put into something is the amount that energy it changes by. And if there's a level road that it's on, in this case, I mean, it's not changing height. That's to say that none of that energy is going into potential energy. There's no springs. Shouldn't it all go into the kinetic energy of the cart? Right? Like whatever work you do on something, it should go into the kinetic energy if it's not going into height change or springs. Right? So hold on a minute. That's not what's going on because the cart was going constant speed, wasn't it? Didn't it say constant speed? But that's okay because of what other detail? The friction force on the cart, right? So there was a question B. This is question A right here. That's the answer to question A. Question B says, what is the net work done on the cart? As if the cart's just going constant speed and it's on a level road, then doesn't it have the exact same mechanical energy at the end as it started with? So whatever that works in terms of kinetic energy, 1/2 mv squared. If you knew the speed of the cart, 1/2 mv squared, and it would be the same both places. So part B, I'm going to do part B in 2 parts. Right? I'm going to lead into that with this. What's the work done by the friction force? Well, isn't it like the same setup here because the magnitude is the same, except for one thing. The direction of motion of the cart and the direction of the friction force are exactly opposite of each other, aren't they? It's almost like there's a 180-degree angle between those two force vectors, or between those two vectors, the force vector and the distance vector. Guys, what is cosine of 180 degrees? It is -1, okay? And that's sort of another way to think of it. So what's the work done by friction equal to? -4330 joules, right? So the friction is doing negative work on the cart. Okay, that's how this is all coming together. Because the shopper is doing positive work on the cart, the friction force is doing negative work on the cart. Therefore, the net work on the cart, this is the actual question, is how many joules? 0 joules. There's 0 net work done on the cart. Okay. You guys get that? How are we doing here? We got till, oh, I think we're, okay. Number 5, starting from rest, a block of some mass slides some distance down an incline at some angle. The coefficient of kinetic friction between the block and the incline is this number. And there's a series of questions. Find the work done by gravity, the work done by friction, the work done by the normal force, and then there's a question after all those. So one thing at a time here. I think I'm going to solve this one in terms of variables, which means that it doesn't matter what the textbook numbers are, you just plug in whatever you want. Give you guys a general solution. Okay. So let's get an incline going. I'm gonna do this over 2 pages of paper, right? One for the picture and then one for like any math work I have to do. Okay. So I got this block. Let's see what numbers they gave you. They gave you the mass of the block. I'll call that M for mass. Okay. They said the distance that it would slide down the incline. So I'm gonna call that distance L, like L for length. Okay. They told you the angle above the horizontal that it's pitched at. So I'll just call that some general theta. They also told you coefficient of friction. So this there's some coefficient of kinetic friction as it's sliding. And in the back of your mind, you know that there's some gravity field. So something like that, right? Okay. So, okay, we're juggling these 5 variables, 4 that were explicitly given to you, 1 that you know in the back of your mind exists. First question, what is the work done by force of gravity? Work done by gravity. No, a few ways to think about this, but part A, work done by gravity. It's some version of force times distance, isn't it? Force times distance. Right. That's a dot product, maybe something to do with cosine, something like that. Right. Now, here's where things get a bit tricky. Is okay. The gravity force, isn't that the weight of this block? Maybe we should do a free body diagram real fast. Let's get one real fast. You guys have done like a bunch of these, so there's mg pulling down. There's a normal force this way, which should just be mg cosine theta. Right? I mean, you guys have done enough of those that you can figure that out. Okay? And then there's a friction force, which is coefficient of friction times normal force. Okay, so you guys know that. And if this block is okay, so good stuff. All right, so I see the force on the block. The force on that block is just mg, isn't it? Okay. And what about the distance? Well, the block moves a distance L, but gravity is not pulling in that direction. Doesn't gravity only change its height? Right? So I need a height value here. Now here's where gotta. If you step to the book equation, you might say, oh, that's L times cosine theta because it's a dot product and we need the cosine. Right? That would actually lead you astray. This is not L cosine theta. What is the height change? It's L times what? Sine theta. It's actually L sine theta. Right? Hold on, man. I thought the textbook definition was cosine theta. Right? Here's a perspective on that. Okay, so the actual height change in the direction of the gravity pull, right? That is this expression. Right? Why is it sine, not cosine? Because this angle is not the angle between the direction of motion and gravity. This theta is the angle between the direction of motion and the horizontal. Gravity pulls perpendicular to the horizontal. So the angle we actually care about might be this angle up here, which is 90 degrees minus theta. Do you guys know that? Here, a little side note. I don't know if you guys remember this from a math class, but if you have cosine of 90 degrees minus theta, that's the same thing as sine of theta. Right, little side note here. Let me prove that to you guys. What if this was a 41 degree angle? What is sine of 41 degrees? That's 0.656. What is cosine of 90 minus 41 degrees? 0.656. It's the same thing. Right. So, a few perspectives on that. But that's it. That's the answer to part A. The work done by gravity is this expression here. MGL sine theta. MGL sine theta. It's look a little prettier like that. Part B. What's the work done by? Wait, am I doing something? Okay. Slides down. Okay, work done by friction. Okay. So that was part A. Part B. Work done by friction. Okay. Now, the friction force is actually in parallel to the direction of motion, isn't it? It's just 180 degrees from it. Like the direction of motion of the block and the direction of the friction force are exactly opposite of each other. That reminds me of the Schopper question, where the friction force is opposite of the motion. Do you think this is going to be a negative answer? You could think of it that way. The cosine of 180 degrees would give you the negative sign. So why not just throw it in here now? So it's negative force friction multiplied by the full length that it moves, right? Is that okay? Right. So we're just thinking along the axis parallel to the surface. Right. Now that's okay answer by itself, except that it's not in terms of givens. Well, the L was given to you, but not force of friction. So let's do a series of substitutions. Do you guys remember that would be coefficient of kinetic friction times the normal force? Is that okay? For friction, you can substitute. Okay, and they give you coefficient of kinetic friction. That was one of the given values. But not the normal force. But that's okay because you guys know normal force. I mean, you guys have done so many of these that hopefully that stands out as being, okay, that's got to be mg cosine theta. Is that right? Okay, so then, well, put it all together, the negative, here's a mu k, here's an mg. I guess you can put anything in any order you want. L, cosine theta, whatever. Some version of that. Okay. That is the work done by friction. Okay. Ooh, so if you added these two together, wouldn't that be the net work done on the block? Okay. What if the block was in equilibrium, like it sized out at constant speed? Do you think that these two terms would be exactly opposite of each other and that would zero out, give you zero net work? Or probably, maybe something like that. So the block would not speed up. It was negative energy change. Okay. Part C says, what is the work done by normal force? Work done by the normal force. Okay. Well, guys, the direction of the motion of the block and the direction of the normal force are perpendicular to each other. So, sort of by definition, what does the answer to this have to be? Zero joules. Right? That normal force is not pushing the block in the direction of its motion. Okay? The normal force usually does zero work on the object. If the object is like sliding parallel to the surface, something like that. Okay. Qualitatively, how would the answers change if a shorter ramp at a steeper angle had been used? Okay. Let me do this, okay? Because I don't know when they're going to call you guys to the pep rally, so let's do this. Okay. You guys see the original ramp and the steeper ramp with the shorter angle? Okay. So if you compare the work done by on each one by gravity, okay. So if you're watching the video at home, take a good look at that. The answer is like one step away. For you guys, we're going to cover this. We'll pick up there next week.